Hi, myself S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss, we will have a question bank discussion on input-output organization and memory organization. So the first question is explain explain with the block diagram the DMA transfer in a computer system. So DMA controller. So we are explaining about the DMA transfer with a neat block diagram. So DMA means direct memory access. So this direct memory access, it is performed by a controller that is called DMA controller. So the DMA controller is a hardware device that allows IO device to directly access memory with less participation of the processor. So the DMA controller, it performs a method that is called direct memory access. So direct memory access means this method, it allows an input or output device to send or receive the data directly to or from main memory, bypassing the CPU to speed up the memory operations. So this direct memory access, it allows the IO devices to send or receive the data from the main memory. So without involvement of the CPU. So that means we in this process we are bypassing the CPU because the CPU, it doesn't allow large amount of data transfer through the CPU. So because it takes some time. So that's why we are bypassing the CPU so that the IO device can send or receive the data directly from the main memory using this DMA controller. So removing the CPU from the path and letting the peripheral device manage the memory buses directly would improve the speed of transfer. So by using this direct memory access method, we can improve the speed of transfer because we are bypassing the CPU so that we can directly transfer the data from the IO device to the memory. Okay. So this transfer technique is called direct memory access. So during this DMA transfer, the CPU is ideal and it doesn't have any control of the memory buses. So inside the processor, inside this entire DMA controller, we have different buses. System buses are there, address bus, data bus, control bus. So when the CPU is ideal, so the CPU, it doesn't have any control over the all these buses. So that means all these buses will take care by the DMA controller. Okay. So a DMA controller takes over the buses to manage the transfer directly between IO device and the memory. So here you can see the block diagram. So how the IO device is transferring the data directly to the memory, whether it can transmit or receive the data directly from the main memory RAM. So without involvement of the CPU. So this is a position of DMA controller among the other components in a computer system. So we have IO peripheral devices, DMA controller, CPU, and the main memory RAM. So we are transmitting the data or receiving the data to and from the main memory. So that means the IO device is transferring the data to the memory without involvement of the CPU. So that the technique is called direct memory access. So let's see the sequence of steps followed during the data transfer process. So when the IO device, it is ready to transfer the data, first it will send the IO device, it will send a request signal to the DMA controller. So that is a request signal is called DMA request. So whenever the DMA controller it receives DMA request, then the DMA controller will send a bus request signal to the CPU. So it will send a bus request signal. So through this line. So BR means bus request. So when the CPU it receives bus request, so when if the CPU is decided to give the control of the buses to the DMA controller, then the CPU will send a bus grant signal. So the CPU will send bus grant signal to the DMA controller. So that means when BZ is equal to 1. So that means the bus granting is given to the DMA controller. So that means all the data bus, address bus, and the control buses of the CPU are disconnected from the CPU, and all these buses will take care by the DMA controller. So now the once the DMA controller it receives a bus grant signal, then the DMA controller will send an acknowledgement to the IO device. So whenever the IO device it receives a DMA acknowledgement, then IO device or IO peripheral device will starts transferring of data to the memory. So it transfers the memory, it transfers the data to the memory through this through the data bus. Okay, so once the data transfer is completed, then the DMA controller will send an interrupt signal to the CPU. Whenever the CPU it receives interrupt signal, then the CPU will take care so that the DMA controller will release the buses and the CPU will take care of all these buses. So in this way, only the CPU will involve only during normal operation. So when we are transferring any large amount of data, the CPU is not involved in because we are bypassing the CPU when when the IO device is transferring large amount of data to the main memory. So this process is called direct memory access. So next question: identify the function of DMA IO operation and also show the input or output processor. So direct memory access, the data transfer between fast storage media such as magnetic disk and memory unit is limited by the speed of the CPU. So in direct memory access, the data transfer between the fast storage media such as magnetic disk and the main memory unit is limited by the speed of CPU. So that's why we are bypassing the CPU. So that means we are not passing the data through the CPU. So we are bypassing the CPU so that we can transfer large amount of data from the IO device to the main memory without involvement of the CPU. So this is a efficient way, okay, and it is a faster way to transfer the data from the IO device to the memory directly. So thus we can allow the peripherals directly communicate with each other using memory buses, removing the intervention of the CPU. So this type of data transfer technique is known as DMA or direct memory access. Okay. So during this DMA, the CPU is ideal, and the CPU it doesn't have any control over the system buses. And coming to the input or output processor. So in a computer we have two types of processor. One is the general purpose processor, and another one is the input or output processor. So this input or output processor it performs the operations related to the input or output devices. That means they are specially designed to perform the operations related to the input or output devices. Whereas the general purpose processor it can be used to perform all the various operations that include arithmetic operations, logic operations, and shift operations. So the main memory unit takes the pivotal role. So the main memory, it takes a pivotal role because if you open any applications or if you run any application that is running from the main memory itself. So that's why the main memory, it takes a pivotal role. So it communicates with the processor by means of DMA. The input or output processor is a specialized processor. So it is IO processor it is a specialized processor which loads and stores the data into the memory along with the execution of the IO instructions. Because it is a input or output processor. That means it involves in processing of the operations are related to the input or output devices. So if you want to read the data from the input device, we are using the instruction called in. And if you want to transfer the data to the output device, we are using an instruction called out. So these are the two instructions that are used to load and store the data into the memory. Okay, so using this in and out instructions, either we can read the data from the input device or we can send the data to the output device. And this IO processor, it acts as an interface between the system and the several IO devices. It involves a sequence of events to executing IO operations and then store the results into the memory. And coming to the parallel, illustrate the parallel priority interrupt with a block diagram. So parallel priority interrupt. So that means interrupt. So interrupt means something which breaks the routine. So that is called interrupt. So parallel priority interrupt. So in the computer, if only one interrupt is there, then the processor can execute it. But if more than one interrupt is there to the processor, then the processor may confuse. So which interrupt it has to be performed first, then next. So to avoid that obligation, so we are assigning a parallel priority. Parallel priority. So that means if more than one interrupt occurred at a time, then we are assigning some priority. Suppose if multiple interrupts are there, I0, I1, I2, I3. So these are the several interrupts. So suppose if only one interrupt is there, no problem. But if more than one interrupt is there, then the processor may confuse which interrupt it has to be serviced first. So for that purpose, we are assigning priorities to the interrupts. So 0 is the having highest priority. It is having highest priority, and 3 I3. So 3 is having the lowest priority in this scenario. So whenever if all interrupts are occurred at a time, I0, I1, I2, I3, then because since the I0 is having highest priority, so the CPU will service the I0 interrupt as first priority. After that, I1, next I2, I3. So in this way, all the interrupts will be serviced based on the priority. So the parallel priority interrupt method uses a register whose bits are set separately by the interrupt signal from each device. Priority is established according to the position of the bits in the register. In addition to the interrupt register, the circuit may include the mask register, whose purpose is to control the status of each interrupt request. The mask register can be programmed to disable lower priority interrupts while the higher priority device is being serviced. So when the highest priority interrupt is servicing, then all the lower priority interrupts will be disabled, because always the interrupt with highest priority will be serviced first, then the next priority, and so on till the lowest priority. So this is a priority logic for a system of four interrupt sources. Okay, so here the interrupts are generated by the several input or output devices. So in this scenario, we are assuming four such input devices are there. The first device is a disk, next printer, reader, keyboard. So these are the various input devices, and these are various input or output devices. Then these are generating the interrupt to the processor to service it. So we have a interrupt register and mask register. So interrupt register, since we have four IO devices, we are using a 4-bit interrupt register, and we are also using the 4-bit mask register. So mask register we are using for the controlling purpose, for the controlling of the interrupts. And the interrupt register is used to store the its interrupt values. So whenever the interrupt is occurred, that corresponding register will store uh, one as a the interrupt. Okay, and all the outputs of interrupt register and mask register are given to the AND gate, and the output of the AND gates are given to the 4 by 1 4 by 4 by 2 priority encoder. So 4 by 2 priority encoder. So the inputs are 4, I0, I1, I2, I3, and outputs are 2. So these are the output 1, output 2. So why not Y1? Okay. So it is a priority encoder. So according to the priority, it gives the output. So that is a priority encoder. So here you can see the truth table of the priority encoder. So we have inputs, four inputs, I0, I1, I2, I3, and we have two outputs. So you can you can label as this is X and this is a Y. So X and Y are the outputs, and IST, interrupt status bit, interrupt status bit. So if interrupt is occurred, then the status bit will be set to 1. If no interrupt, then the interrupt status bit will be set to 0. So according to this, here when I0 is interrupt is occurred. So that means the first device is interrupt generated. Then that interrupt will be stored in the 0th bit of the interrupt register. Then that will be applying to the AND gate. Okay. So suppose if all devices generated interrupt, so it will store 111. So in this way, the value will be stored in the interrupt register. Similarly, mask register. Mask register. Suppose if you want to mask a particular value, then we can set the value accordingly. Suppose even if the mask register is 1111, then what will be the output of the AND gate? So since all inputs are 1 1, we will get logic 1 as the output of the AND gate, because both inputs are logic 1. So for the AND gate, the output is equal to 1 for the input if any one of the input is logic 1. So according to that, all the outputs of the AND gates are 1. So here, four devices raised the request at a time. Okay, so we have set the priority. So like 0 is having the highest priority and 3 is having the lowest priority. So since 0 is having highest priority, the I0 corresponding code will be generated at the output of the priority encoder. Okay, so see here, when I0 is generated interrupt, then the output is 0 0, and the IST bit is equal to 1 because interrupt is generated. So that's why IST is equal to 1, and the output of the priority encoder is 0 0. Okay, because when the I0 is 1, no need to check the further devices because I0 is having the highest priority. Whenever the highest priority interrupt is generated, it has to be serviced first, then the next priority, so on so on. Okay, so here I1, I2, I3, no need to check. So D represents don't care. D represents don't care. That means either it could be a 0 or 1. So even if all ones in I1, I2, I3 places, it doesn't matter. So only the I0 will be considered because the I0 is having the highest priority. Okay. So in this way, all the corresponding codes will be generated. Suppose if I1 is generated, I1 is interrupt generated, and it is I0 is 0, then the corresponding output will be 0, 1. And if I2 is generated, then the corresponding code will be 1, 0. If the third device keyboard, the fourth device keyboard is generated the interrupt, then the corresponding code will be 1, 1. So in this way, we will get the priority encoder outputs according to the input values. And finally, the generated values will be stored in the bus buffer. So this buffer is a 8-bit register. Okay. So here, suppose if the first device is a generated priority, then the x and y values are 0, 0. And here these are the different values. So here these two x and y values will vary according to the input combinations of the priority encoder. Okay, so finally it generated a vector address, and that vector address it will be sent to the CPU for executing the corresponding interrupter. Suppose if disk generated the interrupter, so that the interrupt service routing program related to the disk device, it is stored in this address. So that it will execute the interrupt service routing program which is located at this address. And here we have two flags. One is interrupt enable and interrupt status register. Interrupt enable. So this bit it tells whether the interrupt enable should be activated or not. So if IEN is equal to 0, it doesn't allow any interrupts from the external devices. And if I is equal to 1, then interrupts will be allowed. And similarly IST. So if the interrupt is generated, then IST become 1. If no interrupt is generated, then the IST will be equal to 0. So here as interrupt is generated, IST is equal to 1. So finally the output will be 1, 1. And then that generated interrupt will be sent to the CPU, and then after receiving the CPU, then the CPU will send a acknowledgement. So it will send a interrupt acknowledgement to this interrupt priority logic. So in this way, all the priorities will be serviced by the CPU. And compare the synchronous and asynchronous data transfer. So asynchronous communication and synchronous communication. So in a digital communication, the data can be transmitted from transmitter to the receiver or sender to the receiver in two ways. One is the serial data transfer, and another one is a parallel data transfer. So in serial data transfer, again we have two types of communications. One is asynchronous communication, and second one is synchronous communication. So in asynchronous communication, the transmitter and the receiver it works at different clocks. That means the transmitter and the receiver they will use a separate clock. So one clock is for the transmitter and another clock is for the receiver, and there is no relation in between them, the transmitter and the receiver, with respect to the clock. Whereas in synchronous communication, the transmitter and the receiver they works at the same clock. That means they will share the same clock. Next, in asynchronous communication, we are transferring the data using some start and stop bits. So start bit and stop bits. Okay, so start bit as 0 and stop bit as the logic 1. But in the synchronous communication, we are not using any start and stop bits. Okay, next overhead is more due to start and stop bits. So in this asynchronous communication, the overhead is more because along with the 8-bit data, we are using some start bits and stop bits. So that's why the overhead, the size of the data is increases. But in synchronous communication, it is having less overhead because in the synchronous communication, we are transmitting only the information. We are not transmitting any zeros. We are not transmitting any start or stop bits. So that's why it is having less overhead. And distance limitation is more compared to the synchronous communication. So here the asynchronous communication is using when the distance between the transmitter and receiver is more, and the synchronous communication is used when the devices are when the transmitter and receiver are when they are very near, and no separate clock pin in asynchronous communication, and we have a common clock for synchronization. And next, asynchronous communication is a cheap and less hardware, and it is a synchronous communication is a expensive because we need to use some synchronization circuits between the transmitter and the receiver, because in the synchronous communication synchronization it plays a vital role. So that's why we need to use the synchronization circuits, which makes the synchronous communication is expensive and complex hardware. And examples of the asynchronous communications are RS-232 and RS-485. In synchronous communication, the examples are I2C, inter-integrated circuit, and SPI, serial peripheral interface. So these are the comparison between the asynchronous communication and synchronous communication. Coming to the explain stroke control in asynchronous data transfer along with handshaking problem. So already we have seen the serial data. We can the serial data transfer. It can take place in two ways. One is asynchronous data transfer, and the second one is synchronous data transfer. So in asynchronous data transfer, we are transmitting the data. Suppose if you have a transmitter and a receiver. So from the transmitter, we are transmitting the data at one point of time. After some time, the receiver will be received received the data. So that is called asynchronous. That means the transmitter and the receiver, they are not transmitting and receiving at a time. So that means after some instant of time, the receiver will receive that data. So here we are not using this asynchronous data transfer. It doesn't require any synchronization. Okay, so in asynchronous data transfer, we can transfer the data from the transmitter to the receiver using this strobe pulse. So, what is strobe pulse? Strobe pulse is a control signal, and it is supplied by one unit to indicate the other unit when the transfer has to occur. So, using this strobe pulse, the stove may be activated by the source or destination unit. So this stove pulse, it can be generated by either the source unit or the destination unit. So the source initiated data transfer and the destination initiated data transfer. So we have again two types. First one is a source initiated data transfer. So we have source unit and destination unit. So when the source unit, it will places the data, whatever the data it wants to transfer, that it is keeping in the data transfer. After certain time, the source unit will assert a strobe pulse. Means the source unit will send a strobe pulse to the destination unit. Once the destination unit receives a strobe pulse, it indicates that a valid data is placed in the data bus so that the destination unit will read the data from the data bus. Okay, so that is the operation in the source initiated data transfer. So that means the source here, the source unit is initiating the data transfer. Okay, and the timing diagrams of its corresponding. So first, the data will be placed in the data bus. After certain duration, the strobe pulse will be applied to the destination unit. Once the receiver receives that strobe pulse, it can understand that a valid data is placed in the data bus so that data can be read by the destination unit. And next one, destination initiated data transfer. So in this destination initiated data transfer, the destination unit will initiate the data transfer. That means the strobe pulse, the strobe pulse will be generated by the destination unit. So first, the destination unit will send a strobe signal to the source unit. Then the source unit will places a valid data in the data bus so that data will be read by the destination unit. Okay, so this is a destination initiated uh, data transfer. But we have a major problem with this strobe based data transfer. The drawback is when the source or destination is transferred the data, it doesn't know whether the transmitted data is received by the other unit or not. So that is the main problem with the this strobe based data transfer. To overcome that problem, we are introducing one more signal that is called handshaking. We are, so here strobe is a one signal. So to indicate whether the transmitted data is received by the other unit or not, for that purpose we are adding one more signal that is called handshaking. So using this handshaking method, it can overcome the problem we are facing, what the problem we are facing here. And coming to the illustrate the characteristics of some common memory technologies. Okay, so the key characteristics of the memory device or memory system are as follows. So these are some key characteristics of some common memory devices. The first one is the location, capacity, unit of transfer, access method, performance, physical type, physical characteristics, and organization. So first one is the location. It deals with the location of the memory device in the computer system. So we have total three possible locations, and first one is the CPU, and second one is the internal or main memory, and then external or secondary memory. And coming to the capacity, so capacity is the amount or the total volume of data that the system's memory can store. That is called capacity. So the capacity of any memory device is expressed in the form of the word size and the number of words. So using this two, we can decide the capacity of a particular memory device. So suppose if you have a memory memory like this. So in every memory location, we can store one word. So it represents the number of words. And in this particular location, we can store in this particular location we can store some information. So suppose if we store one, if we store 101100. So it is a 8-bit data. It is a 8-bit data. So that means the word size is the 8-bit, and the number of locations. Suppose if 1024 locations are there, 1024 memory locations are there, then the number of words is equal to 1024. So in this way, we can measure the capacity of the memory device. So the capacity of the memory device is number of words multiplied with the word size. So here in this scenario, 1024 is the number of words, and the size of each word is 8-bit. So this is a total capacity of the memory unit. And unit of transfer. So it is a maximum number of bits that can be read or written into the memory at a time. In case of main memory, it is mostly equal to the word size. In case of external memory, unit of transfer is not limited to the word size. It is often larger and is referred as blocks. And access methods. So access method is a fundamental characteristic of any memory device. And inside the computer, we can access the data in 3 ways, that are um, sequential access, random access, and direct access. Now coming to the organization, it is a erasable or non-erasable. So the memories are mainly classified into 2 types. One is based on this erasable or non-erasable. Okay, so that are the memories in which the data can be programmed. Once programmed, cannot be erased. That are called non-erasable memories. And the memory devices in which uh, we can erase, in which data in the memory can be erased. That is called erasable memory. That means using erasable memory, we can write the program and we can erase it. So we can perform several times these operations. But in the non-erasable memory, once the user programmed the memory device, then the user is not allowed to erase the data. Examples are RAM and ROM. RAM is a erasable and ROM is a non-erasable. And performance. So performance of the memory system is determined using 3 parameters. One is access time, memory cycle time, transfer rate. So access time, it refers to the time interval present between the request for read or write and the data availability. And memory cycle time is defined as only for RAM, random access memories, and it is a sum of access time and additional time required before the second access can commence. And transfer rate. So transfer rate is it is defined as the rate at which data can be transferred into or out of the memory unit. And physical characteristics are volatile or non-volatile. So volatile means if the power fails, then the data stored in the memory gets erased. So that is a volatile. And a non-volatile means even the power fails, the data stored in the memory, it will not lose. So that are such type of memories are called non-volatile memories. So in this lecture, we have discussed various questions regarding to input-output organization and memory organization. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.